going to talk about EPN-Repro2, a reference tropospheric dataset over Europe, and I would like to first acknowledge the co-author of this presentation. And the outline of this presentation is the EPN-Repro2, the second EPN reprocessing campaign, which covers the period 1996 up to 2014. So I would like to describe the features of the individual contributing solution and the combined ZTD solution. And we have evaluated this product versus radiosonde data and the interim data. And we have computed trends and uncertainties. And I'm going to show two examples of data exploitation in climate research. And in case you are interested in, we have also published a paper where all the details are reported. So EPN-Repro2 is the second EPN reprocessing campaign organized in Europe framework, which covers this period, and the aim in order to deliver the homogeneously reprocess site coordinates, velocities, and tropospheric parameters. And in this presentation, we focus only on the tropospheric part. And only 5 out of the 16 EPN analysis centers took part to this campaign, and they are ASI in Italy, the GOP in Czech Republic, IGE in Spain, LPT in Switzerland, MUT in Poland, and we have 5 contributing solutions plus 3 variants. And as regards to tropospheric parameters, we have ZTD and gradients in the individual contributing solution. So in total, we have 5 plus 3 solution obtained with at ASI. We use Gypsy, and we have reprocessed the full EPN network at the GOP with Bernice, with the full EPN network LPT with Bernice, and the EPN subnetwork IEG Bernice with the EPN subnetwork, and MUT with Gamete with the full EPN network. So we have different software involved and the different networks and the 3 main software packages used in the processing. We have 3 Bernice solutions, 1 with full EPN and 2 with the EPN subnetwork, and the 3 solutions with the full EPN, 1 with Gypsy, Bernice, and Gamete. So different software with the same network. But despite the different software used and the different analyzed network, there were also some diversity in the GNSS solution provided by the analysis center, and the impact of which need to be evaluated prior to performing the combination. So in 2 analysis center provided solution with the GLONASS data, and while all the others provided a solution with GPS only, and in some we have solution with the IGS type mean antenna calibration and others with IGS type mean plus EPN individual antenna calibration, and solution which did not entitle atmospheric loading were applied. And as regard the orbits, IGE, GOP, LPT, and MUT use code reprocessed orbits, while at ASI, GPR reprocessed orbits were used. And for the mapping function, we have solution with the global and the Vienna mapping function. So we started looking at this, the impact of this diversity, and we started with the GLONASS. We have GLONASS data starting from 2003, but the number of GLONASS data is started to increase up to only in 2008. And the impact of GLONASS data has been evaluated in terms of ZTD trend analysis. At LPT, they run to exactly the same solution with the same setup, but in one case a GPS-only solution, in another case a GPS plus GLONASS solution, and we look at the difference of the ZTD trends from more than 100 sites, and what we found is that there is no significant rate, and it means that the additional GLONASS observation has a neutral impact on ZTD trends, and it means that these ZTD trends might be determined independently from the GNSS satellite system used in the processing. And this is important, especially if we consider our near future, which we will have Galileo data and Beidou data, and it is expected that this new satellite constellation will not introduce any systematic changes in the ZTD trends. The other was the impact of GIGS type mean and the EPN individual antenna calibration. And according to the EPN guidelines, an analysis center has to use an EPN individual antenna calibration if they are used, if they are available, instead of IGS mean type. But we have about 70 stations in the EPN network where these individual antenna calibration are available. But nevertheless, in this Repro2, we have solutions were carried out only with the IGS mean type. So what we have done is exactly the same as before. Completely two identical solutions, same setup, everything is the same, except this model is changed. And we have evaluated the difference in terms of the difference in the up component and the difference in the ZTD. You will see here that we have a difference in the up. This is just one example for this one station. And you see here that we have a difference, a jump in the up component, ranging from 8.7 millimeters up to minus 5.2 millimeters. And we have also a jump in the ZTD. But this jump in ZTD is, this jump in the ZTD is too small. I don't know how to come back. This jump in the ZTD is too small. It's less than 1 millimeter, and in most in first case, and it is below. It is minus 1.4 millimeters, and for all the stations that we have looked at, these jumps is in the range of 2 millimeters. And so it is too small to be captured during the combination process, where we have set up a threshold of 10 millimeters in the ZTD bias. Because this 10 millimeters threshold in ZTD bias turns into 1.5 kilogram per square meter bias into integrated water vapor. The other things was to see the impact of the non-tidal atmospheric loading on ZTD and height. Again, same setup, two different runs, same setup, just its model is changed. And this is an example for two stations. Sorry for that. For two stations, one is Kiruna in the upper part and Riga in the lower part. You will see in black that there is the displacement in the up component, while in red you see the displacement in ZTD. The displacement in the ZTD is very low. It's in the range of 0.5 millimeters. And the two quantities, as you can see from the scatter plot, are not at all correlated. Once having checked all this diversity, we have started with the combination. The first, it was a very hard work to do, and at the beginning we have done first a preliminary combination, considering all the 8 input contributing solution, and the aim of this preliminary combination was to check the input, to flag the outliers, to send feedback to the analysis center, and it was very tough. And then, in accordance with in agreement with the EPN analysis center coordinator who was responsible for the combination of the site coordinates, we choose 5 input solution, and we choose only those solutions carried out with the Vienna mapping function. So the Vienna mapping function is in common with all these contributing solutions. We have run the combination, and you see here the agreement of each contributing solution with respect to the combination. In the upper part there is the bias, and in the lower part there is the standard deviation. And in the first period, before March 2000, we have the agreement in terms of bias is less than 3 millimeters. Thereafter it was less than 2 millimeters. As an internal quality metrics, we look at the site coordinate repeatability, and this is a long-term, and we set up a threshold of 9 millimeter, which is 3 millimeter ZTD, 0.5 kilogram per square meter integrated water vapor. And on a these are all the EPN station, and on a long-term basis, all the EPN station except one are below this threshold. But this station MOPI, it is very well documented at EPN Central Bureau Euro that this station has been several times excluded from the routine combination, from the routine processing because of bad period of tracking data. Then the external validation was done with respect to completely independent data set. We have the radiosonde data first, and it was done at 183 EPN collocated sites. In this plot, we have the EPN collocated sites are listed, and they are sorted according to their distance from the radiosonde launch site, from the closest to the most distant. And we found a bias, we found an overall bias, which is less than 5 millimeters for the majority of the station, and with a standard deviation which increase from with the distance from the radiosonde launch site. And what is important is that if we done the same comparison using EPN-Repro2 but completed with EPN, we completed with EPN there's something that appears here. Completed with EPN routine data, we have an improvement of about 3-4% in EPN-Repro2. We have done another comparison with other external data, that is ERA interim, and you see here the bias and the standard deviation, and we have a positive bias, which is the blue cycle, which seems to become lower or even negative in the mountain areas. Then, if you look at the standard deviation, there is a strong latitudinal dependence of the standard deviation due to the increase of the water vapor toward the equators. And the other important thing is that if we done the same comparison using EPN-Repro2 completed with the EPN operational data, we have with EPN-Repro2 an improvement of 8-9% in ZTD bias and standard deviation. Now, the question is if this data set is suitable for ZTD trend analysis over Europe, and what is the uncertainties of this ZTD trend. And for this, we have chosen 5 EPN stations among the oldest EPN stations, and we have computed ZTD trends for 3 independent GNSS datasets that are EPN-Repro2, EPN-Repro2, IGS-Repro1, because these are also IGS stations, and we have also added radiosonde data and ERA interim data. From this histogram, you can see that the 3 GNSS datasets are very consistent among them, but the uncertainties, the ZTD trend uncertainty computed with EPN-Repro2 is lower with respect to the other 2 GNSS datasets. And as I have shown you before, the EPN-Repro2 has a better agreement with respect to radiosonde data and ERA interim data than EPN-Repro1. So, but as we all know, the EPN network is a very good coverage over Europe, and it is a better coverage than the IGS network of the radiosonde network that are currently used for the long-term analysis of ZTD and integrated water vapor. So, from these results, we can say that this dataset is suitable for ZTD trend analysis on long basis over Europe in area where the other datasets are not available. Now I'm going to show you 2 examples of data exploitation of the dataset for climate research, which is an emerging field of research. And one is the use of Repro2 in climate model simulation. This is an activity which is ongoing at the Royal Meteorological Institute of Belgium, and they are using Alarau climate model, and they are doing the assessment. This is the Alarau domain, and this is the Alarau domain, and these are within the domain they have chosen 10 100 EPN station on the basis of these two criteria. And why it is important to do an assessment of the climate model simulation? Because this climate data are used for a climate prediction in the future. So you need to know which process situation the model is capable to better predict or which not. And I'm going to show you an example here. You will see there is the comparison of ERA interim data versus GNSS in the lower part and LRAO versus GNSS. You will see that on a monthly basis, ERA interim has a constant bias versus GNSS observation, while LRAO performs much better, except in the summer period, for which there seems to be a dry bias, which is under investigation. Another example is the usage of this data in regional reanalysis. This is an activity which is ongoing at UK Met Office, and in the framework of this European project, Uncertainties in Ensemble of Regional Reanalysis. They are doing a regional reanalysis over the last 40 years in a 4D hybrid data simulation. And this is the bunch of data they are going to assimilate, and in this bunch of data we have also EPN-Repro2 data. Now, these activities have been, the EPN-Repro2 activity has been carried out in close cooperation with the Working Group 3 of the GNSS for Climate, of the Coast Action GNSS for SWEC, but now together we have delivered an EPN-Repro2 dataset which is homogeneously reprocessed, which has been checked, combined, evaluated, but in the time series, in the station-specific time series, we have some jumps, discontinuities due to receiver changes, equipment changes, and this change point needs to be detected and corrected for. So we need to, the story is not finished yet, we need to homogenize this data set, and this will be done in the framework of this IAG working group, GNSS Tropospheric Product for Climate. So, in summary, we have homogeneously reprocessed the full EPN network. We have delivered several individual solutions, and we have evaluated the impact of this diversity, and we have evaluated the product with respect to independent data set. And these data are now in Synex RAW format, unfortunately the old format, not the new one, and can be downloaded from the EPN-Repro2 product directory at BKG Data Center. And if you are interested in it, the EPN Center Bureau, we have uploaded several plots at this web address. And with this, I conclude my presentation.